Hi everybody, welcome to this video entitled Simple Dynamic Model of Power MOSFETs. This is the index of this presentation. We will start with an introduction. We will present the model equations. Then we will implement the model with linear capacitances. We will also see the implementation of the model with non-linear capacitances. And as usual, everything will be illustrated based on QSpice simulations. These are some relevant videos related to this topic, power electronics number 1, when we saw the MOSFET hard switching process. Power electronics number 85, understanding MOSFET parasitic capacitance characteristics. And power electronics 86, modeling MOSFET parasitic capacitances. So if you are not familiar with the dynamic behavior of power MOSFETs, it will be advisable for you to take a look at these videos before proceeding with this one today. This slide shows the motivation of this video today. The goal of this video is to develop a simple model of a power MOSFET. So the idea is, instead of using the complete model that we have from our simulation program, for example in QSpice, we are going to develop our own model so that we will be able to see the currents of the different internal elements of the transistor. And the idea is that this will be useful to better understand the dynamics of the MOSFET transistors, and also especially to better understand the switching process with a more simple model than the one that comes with the simulator. So the idea is, as shown here, we have our transistor, our MOSFET transistor, the different terminals, the gate, the drain, the source, the current through them. This is what we can see from outside when we use the transistor or when we do a simulation. So the model that we are going to implement is as shown here. We are going to model the conduction of the channel using a current source. We have the body diode in anti-parallel, and then we have the three parasitic capacitances between the gate and the drain, the gate and the source, and the drain and the source, CDS here. So now let's see how to implement this model and how to obtain the values of the different elements for a particular MOSFET. Let's start by the behavior of the channel. So we want to model this current source here. If we go to the literature, to the books that we have related to the behavior of MOSFETs, we can see that we have three different zones for the operation of the transistor. In the resistive zone, we have a behavior given by this equation. The current through the channel is a constant K sub M, which is related to the conductivity of the channel, times this expression here that depends on the voltage between the gate and the source, which is the control voltage, the threshold voltage, and the voltage between the drain and the source. And this is the range in which we are operating in the resistive zone. In the active zone, we have this equation here, which is a parabolic expression for the current through the channel as a function of the control voltage between the gate and the source, and this is the condition that we have for the operation in the active zone. And finally, the cutoff zone, when the transistor behaves as an open circuit, so we don't have conduction of current through the channel, so the current through the channel is 0 when the control voltage between the gate and the source is lower than the threshold voltage. So these three regions are very easy to implement, to combine all of them with these conditions using the if statements of SPICE simulators. So with this statement here, we can implement everything. So we start here if the control voltage, the gate voltage is lower than the threshold, the current through the channel is 0. And if not, then we have this other if statement that generates this behavior here in these two zones. For this, we compare the drain voltage with the gate voltage minus the threshold value, and in this case we generate this expression, which is this one here, and if not, we generate this other expression. So we can see that it's really easy to implement this behavior in SPICE simulators. Note that here, in order to simplify, we are considering that the source is going to be connected to the ground, so the gate is equivalent, the voltage at the gate is equivalent to the voltage between the gate and the source. So now how to calculate the value of the constant K sub m. We can calculate this constant from the channel resistance that we want for our transistor. For this, if we operate in the resistive zone, we have this expression. So the resistance of the channel is the voltage across the channel divided by the current through the channel. So we have this equation, and the resistance in this area here for small values of VDS. This is when VDS is much smaller than twice the difference between VGS and the threshold voltage, can be approximated by this expression here. So now, for example, in this case, for this transistor IRF 640 that we are using in other videos, this transistor is from ST, but note that we are not endorsing any manufacturer on this channel. We are just using this transistor as an example because this is the transistor that comes with QSPICE. So in this case, for this transistor, we have that the threshold voltage is this value, typically is 3 volts. So this is the value that we are going to consider. And the static drain source on resistance for a gate to source voltage of 10 volts and a current of 9 amperes is typically 0.15 ohms. So this is the value that we are going to consider. So this is the resistance, the gate voltage, the threshold voltage, and then using the expression in the previous slide, we can get this value for K sub m. And now we can do a quick simulation to see that everything goes well. So here we have our model. This is the behavioral current source that we are using to implement the current through the channel. Here is the expression that we have just seen. We have the body diode. We have just used here a regular body diode with a forward voltage of 1 volt. 5 million resistance. So we are not right now very interested in modeling the body diode perfectly. We have also the capacitances. We are going to see later how to obtain these values. And what we are doing here is to apply a sinusoidal voltage source between the drain and the source to go through all the points, the operating points of the transistor, and these for different values of the gate to source voltage. So here we are applying a continuous voltage, a DC voltage, with different values as we are showing here, 4, 6, 8, and 10. And with this, by measuring the current here through this resistor, is the current entering the transistor, and plotting it versus the drain voltage, the drain to source voltage, we can get the different characteristics. So this is in green the characteristic for 4 volts, 6 volts, 8 volts, and 10 volts. So in our case, if we calculate the point that we used in previous slide, then we can measure a channel resistance of 0.17 ohms, which is very similar to the value that we used in previous slide, which was 0.15 ohms. And we have also to note that in our simple model, the value of K sub m also defines the transfer characteristic. This is the characteristic of current through the channel versus the control voltage VGS. So this is the expression that we have for this relationship. As we have seen in previous slide, this is the region in which we have this behavior is in active region, and from it, by taking the partial derivative of the current with respect to the control voltage VGS, we can get the small signal transconductance in our model. So this is the slope of the curve at each point, and is this value here, which is twice the value of K sub m times the control voltage VGS. So the transconductance is not constant, it's going to change depending on the control voltage VGS. And now we can check the transfer characteristic in our model, and for this what we do is to apply a sinusoidal voltage between the gate and the source. So we are going to change with this expression the voltage between 0 and 20 volts at 100 Hz, these low frequencies, in order not to affect the behavior due to the parasitic capacitances. We want to obtain the static behavior of the transistor now, and then by plotting the current going into the drain versus the voltage VG, as we can see here, we obtain the transfer characteristic. So we see the threshold voltage is around 3 volts, and at a given point, for example here, we get 7.3 volts and 9 amperes, and if we use the equation in our model with the value of K sub n that we have calculated, then we can get approximately the same value of the current. We can also compare the transfer characteristic that we have in our model, which is this one here, with the information given by the manufacturer in the data sheet. So here is the value of the forward transconductance for a current through the drain equal to 9 amperes. We get a minimum value of 7, typical value of 11 Siemens. So in our case, for 9 amperes, we have 7.3 volts VGS with the value of K sub m that we have. This is the value of the transconductance. This is this expression. So if we substitute, we get a value of 7 Siemens amperes per volt, which is similar to the value given by the data sheet. And now we can add the values of the parasitic capacitances of the transistor. For this, we can go to the data sheet, and there we can get the value of the 3 capacitances: the input capacitance, the output capacitance, and the reverse transfer capacitance. The manufacturers provide these values for a voltage between the drain and the source of 25 volts, as we know, and for a testing frequency of 1 MHz, and with a DC voltage between the gate and the source equal to 0. So these are the typical values that we get from this information, and from it we can get the gate to drain capacitance, which is equal to CRSS, the reverse transfer capacitance, 60 picofarads. The gate to source capacitance is the input capacitance minus the reverse transfer capacitance, CGD, in this case 1.14 nanofarads. And finally, the capacitance between the drain and the source is the output capacitance minus the reverse transfer capacitance. And in this case, we get 140 picofarads. So with this, we have completed our linear model of the MOSFET. So this is the complete schematic, and here we have the parameters of the transistor. This is the definition, as we have seen, of the current source, and this is the model that we are using for the body diode. So now let's do a simulation to test our transistor under hard switching operation. So we are connecting an inductor with a series resistor, a freewheeling diode, and we are applying a PWM signal to the gate. The switching frequency and duty cycle is 100 kHz, 10 microseconds for the switching period, and the duty cycle is 0.5. The voltage here is 50 volts and this resistor is 5 ohms. So the DC current that is going to circulate through the inductor is 5 ohms approximately. And here we are plotting the different waveforms. So now we can run the simulation and see the results. And here we have the simulation results. So we can see that the current is approximately 5 amperes. This is the voltage across the switch. This is the gate signal. And here we have the product of the voltage between the drain and the source times the current that is going into the drain, the current through this resistor here. So now, for example, let's take a look at the turn on process. So we can see the effect. Here we have the Miller effect. We can check the voltage. So we can see that when we get approximately 3 volts here, 3 volts at the gate, the current through the switch starts increasing. Then we enter into the Miller region here, the Miller plateau. So the voltage is decreasing. So we have a superposition here of current and voltage. We can do this even a little bit greater. And below we can see the power that is being dissipated during the turn on process. So we can do control and click, right click here and do the integral. We can get the energy that is being dissipated in this process. And also we can take a look at the turn off process here. And then we can see again the Miller effect, the increasing in the voltage during this interval at constant current, and then the decreasing in the current. And again, we have here the dissipation that we are going to have during the turn off interval. Again, we can calculate here doing the integrate, and then we will get the energy that we are dissipating during the off interval. Now we are going to do a comparison between our transistor here, our model, and the model that comes with QSpice, the complete model IRF640. The circuit is exactly the same, and we are going to plot the different waveforms together for comparison. So let's run the simulation again. And here we have the result. So let's do a zoom here for the turn on process. So in red we have the response of our model, and in green we have the response of the QSpice model. So we see that we have the same value here, but the time constants are a little bit different. Also here the waveform in blue is our model, while the waveform in green is the model corresponding to QSpice. So again we have a difference. The decrease of the voltage is much slower in the case of the QSpice model. Here is the current. Again, there is some difference, and also here we have some difference in the energy dissipated. So we can do a comparison. Here we do the integrate here for the QSpice model, and then here for our model. So we have 2.6 microjoules compared with 1.3 microjoules. It's something similar, but it's not exactly the same. Of course, this area is much smaller than this one under the blue line. Let's take a look at the other process, the turn-off process. Again, we can see some differences. The time constant here is much slower. But again, the model is simple and we can also understand with it the behavior, the switching behavior of the transistor, and we will see this. We will use this model in future videos to understand the switching process in MOSFET transistors. So now we will try to improve our model by adding the nonlinear behavior of the capacitances. So in previous videos, power electronics number 85 and power electronics number 86, we studied the parasitic capacitances of this transistor, of the same transistor, IRF 640. And we also studied how to model these parasitic capacitances. And this is the model that we are going to use today. So in this previous video, we obtained the parasitic capacitances of the transistor, the three parasitic capacitances. So today we are interested in getting the parasitic capacitances between the gate and the drain and the source, and the gate and the source. And we obtain them by doing these operations, as we have just seen in previous slide. So with these voltage sources, we can do the plotting of the three capacitances as a function of time, but now time represents voltage, so from 0 to 50 volts. And then we have CGS, which is almost constant and equal to 1.22 nanofarads. And then we have CGD in blue and CDS in red. So now we are going to find expressions to model these two parasitic capacitances. And then, as we saw in this previous video, we are going to use this simple expression to model the capacitances. So is the capacitance at a given voltage is the square root of V sub 1 divided by the voltage and times the capacitance C sub 1. So what we are going to do is to try to model the capacitances curves so that they are more accurate in this part at high voltages, because is in the region in which most of the transition, the turn on and turn off transitions take place. So we are using these values for CGD. We are plotting here with this behavioral voltage source. And then here we have the actual value obtained before from the QSPICE model, and this is the approximate value that we get with this expression. And same thing for CDS, this is the point that we are using, this is the expression. Here in green we have the actual characteristic, and in blue we have the approximation using this equation. And here finally we have our complete nonlinear model for the MOSFET transistor. So we are adding a constant value here for CGS, as we have seen, 1.22 nanofarads. This is the expression for the capacitor between the gate and the drain. And here we have the expression for the capacitor between the drain and the source. We have seen how to model these nonlinear capacitances in this previous video using the expression of the charge of the capacitor. And note that these capacitances, especially CGD between gate and drain, depends on the voltage between the drain and the source, because we have modeled it in this way. So this is not a function of the gate to drain voltage. We have developed our model of these capacitances using the voltage between the drain and the source. And also for CDS, of course, is the voltage between the drain and the source, which is the same voltage that we have across the capacitor. So let's try now this model to see how good it is in comparison with the model that we have in QSPICE. Here we can see the complete model using the nonlinear capacitances. We can see the expressions, and here we have the model corresponding to the QSpice component. So again, we are going to plot together the different waveforms. So now we can run the simulation. And here we have the simulation result. So this is the gate voltage, the voltage across the switch, the current through the switch, and the power. On this scale, they are very similar. Let's do a zoom to see the turn on process. So here we can see the waveforms. This is a little bit more accurate in this case, more similar to the actual value. And also here we can see that the transition is more similar too. This is also quite similar, and then the losses seem also to be quite the same. So we can do the math now, do the integral, and for the other one. So we can see here that for our transistor we get 2.1 microjoules, and for the QSpice model we get 2.5 microjoules, so it's very similar. And now for the turn off process, we do a zoom here, and then again we see that there is some difference. This time constant is a little bit slower, this time is greater, so we have some time difference here, but the process is very similar, and also, as we can see, the losses are also very similar. So maybe we can do the calculation now and do integrate here and here. So this is QSpice model 4.7 microjoules, and this is for our model 2.8 microjoules. So we have seen that the results are better. We have improved our model. Maybe in the future we can try to model better the nonlinear capacitances with a more accurate expression, so we are getting a good accuracy at low voltages and also at high voltages, and with this we might get a better approximation between our model and the model from QSpice. The real objective of our model, our simple model, is to be able to use this model to understand later the switching process that we have when driving a MOSFET transistor. Well, with this we get to the end of this presentation today. I hope that this information is useful for you. Please let me know if you have any comment or question regarding this video through the comments box of this video. Thanks for watching, and I hope to see you in the next video. Goodbye now.